Hey everyone, it's Nate. I hope you're having a good week. This week is all about bigO notation, search and sort algorithms, and pseudocode. If you don't already know about bigO notation, it'll come up in interview questions. It's important for designing algorithms and code. And what it is it's an estimate of how long something is going to take to run. So we can use it to evaluate what is the best way to implement an algorithm, or the most efficient way to do so. The O in bigO stands for order, so you can think of it as this function or this algorithm costs on the order of something to run. So the bigO runtime is an upper bound on how long a program, algorithm, or function will take to run, and it's tied to the number of inputs that we have. So you can also use bigO notation for figuring out how much memory a program is going to take, but we're not going to get into that in this class at all. But if you're interested, that also is an important topic that comes up in programming in computer science. There's different ways you might see this written. Usually it's like a big O, parentheses, X or N. Sometimes the O is italicized. There's also this fancy curly O that has a break here. All those things mean order. So I'll start off with a simple example, and that is f of x equals x. And that's a very simple function. The bigO runtime is order x, but you could also technically say the bigO runtime is x squared or x cubed, and so on. Any function that is bigger than the original function could be considered the order of that function. But typically we want to take the smallest reasonable bigO runtime so that we can put sort of an upper bound to our runtime. So let me show you some plots to kind of explain this better. So one easy way to plot things is to use wolframalpha.com. This is Mathematica, but it's online mostly for free. So we can do things like plot x and x squared. So if you remember, I said x could be considered order x squared. Let's change the limits to go from 0 to 100. So we can plot x and x squared. X is this blue line that's almost flat, and x squared is this steeply increasing parabolic function. So we can see that x squared at any of these x values is always greater than x. And that's why we can say that f of x equals x is order x squared, because this x squared function is always bigger than x. In the book, and technically mathematically, you have to give it a lower bound so that the function x squared is always bigger than x is only actually true above 1. So you'll see that it crosses over at 1. So actually from 0 to 1, x squared is actually less than x. So you have to say any value above 1. The function x could be considered order x squared. In the book, they call those things witnesses. And that minimum number that we have is k in the book. And there's also the constant c, which let me just pull up the definition in the book. So there's this constant c that goes in front of our whatever we consider the order of our function. So those are details that are typically only relevant more on the math side as opposed to the programming side. So usually for programming, we're assuming x goes to infinity. Obviously we have to run each program or each loop at least one time. So our minimum k is usually 0. But we're more interested in how these things are performing once we scale up to really large numbers like millions or billions of users, or maybe database queries or something like that. Like I said, I like to plot things, and in the book, chapter 3.2, figure 3 has a plot of a bunch of different functions, so you can see which ones have the lowest order and which ones have the highest. You'll notice the y-axis here is doubling at each tick mark, so that's just a detail that you should be aware of. So the lowest order operation is order 1. So this could be like this would be like an if statement for a bit. So if a bit can be 1 or 0, if we want to check if the bit is 1, that's an order 1 operation because we're just doing one thing. We step up in complexity as we move up this graph. So log n is the next, and then n, which is just the linear function, is next. Like I said, x squared or n squared is greater than n, and the worst case that's typically out there is n factorial. And of course there could be worse things than n factorial, like n to the n to the n, but those don't come up very often. There is another rule in the book, and it's right below this figure. N to the d is order b to the n, but b to the n is not order n to the d. Here's a plot of basically one of those examples. So n to the 10th and 2 to the n. N to the 10th is this blue line, 2 to the n is the purple line. So you can see that above a certain minimum value, 2 to the n is much larger than n to the 10th. So n to the 10th could be considered order 2 to the n. Anything raised to the n power or the x power is always greater than n raised to any power. Another thing to know is that for polynomials like this equation, so if we have x to the third plus 500x, that's order x to the third, because that's the biggest term in this entire equation. So we can plot x to the third plus 500x and also plot x to the third I think we can't see x to the third because it's too small. You can do a semi-log plot by putting log in front of there. There we go. So let's go to like 10,000. And you can see that as we go out to really large numbers, these two functions are essentially the same. The two lines are pretty much on top of each other. So this smaller term doesn't matter as we go to infinity because these bigger terms completely wash it out. So any sort of polynomial or function with multiple elements is always dominated by the largest term. And so you can say the order is that largest term. So another example would be something where we have a log of x squared and x. The order in this case is x because these exponents in a log can actually be carried down to in front of the log. If you don't remember how this looks, so if we have log of x squared, that equals 2 times log of x. And that's just a property of logarithms. So if you don't remember that, that's how it works. So anytime we see these logs here, typically in computer science or in this book, they're almost always log base 2. If you don't remember logs are, I linked to the definition in the lecture transcript here. So the definition on Wikipedia for a log, the exponent by which b must be raised to yield x. So the equation for it's right here, b to the y equals x. So log base b of x equals y. So that's what the log is doing if you forgot. In computer science it's almost always log base 2 because of bits, because bits can be either 0 or 1. There's 2 possibilities. So that's just something to know and be careful of, especially if you're using Wolfram Alpha to plot things. So maybe you want to plot log of x and x. Wolfram Alpha log base x is base 10. If you want to do log base 2 or any other base, I'm not sure about any other base, but at least base 2, you can do log 2 of x, and it will plot log base 2 of x. Yeah, so we can see log of x here is actually 10. Log base 2 of x is a little bit bigger than log base 10, and then here's just x. You can also check on Wolfram that your input is what you expected by looking at the input interpretation. So sometimes, I think with log base 2, if you put an x in front of it without a multiplication symbol, it will actually screw it up, so it's taking the log of 2. So just watch out and always check that Wolfram is actually interpreting your input as you expect it. If you remember from this plot in the book, n is greater than log of n, especially as we go to infinity. So if we have a function like log of x squared plus x, it's order x because x is the biggest term in the equation. But if we have an exponent externally on the log, it's different. We can't bring that exponent down in front of the log. Okay, so that's kind of a general intro to big O notation and what it means and how I sort of think about it. I like to think about it visually, so definitely utilize tools like Wolfram Alpha to plot these things and understand them better. Use it for the homework if you need to, or even the midterm or final. So now I want to give you some tips on the homework because some of it's a little tricky and requires some tricks that I'm not sure they really discuss in the book. You might have a different number than 9 for this problem, but we're trying to find the witnesses, the constants c and k for this function such that that function is order cx squared whenever x is greater than k. So this is following that strict textbook definition for big O, and we have these different options, 4 different options for c and k. So there's a couple different ways to do it. One way is to take these numbers and plug them in. So you can try 1 for x, plug in 1 to this fraction, you'll get a number. 1 squared is 1, so then you'll get a number for the left side, and you can figure out which constant this inequality is true for. Another way to do it is a little more tricky. Okay, so we start off by noticing that all of our k's are 0 or 1, so that means x is always positive. So that means we can get rid of the absolute values because both sides of this equation are always going to be positive. So now what we can do is use a property of fractions that is when the denominator of a fraction gets smaller, the fraction overall gets bigger. So we can take our f of x, which is this, and say that it will always be smaller than the same thing without the 1 in the denominator, because as the denominator gets smaller, the fraction gets bigger. So we can cross out one of these x's, and now we have x squared over 2 plus 1. So we'll start off with the k equals 1 because it's 3 of the 4 possible answers. So what that means is x is greater than 1. So that also means x squared will be greater than 1. So we can take this equation and we can substitute in an x squared for the 1 and say that that will always be greater than x squared over 2 plus 1 because we just said 1 will be less than x squared. Okay, so now we see that our f of x has to be less than this. equation, and if we simplify that, it equals 3/2 x squared. So that's pretty much how you can do that problem without substituting in numbers. There's one other way you can also do it, which is to plot the equations. So I've already plotted the g of x and the f of x here. So you can see that with the coefficients, with c is 1, these things cross over right about 1. So I think that was c equals 1, k equals 0. So we can see that in between 0 and 1, actually our f of x is larger than the g of x, so that cannot possibly be true. We can also then plug in these coefficients and see how they look and see which ones actually make sense and which ones don't. So at least for this c equals 1/2, anywhere above x equals 1, we can actually see our f of x is greater than our g of x until we hit about 4. So we know that the 1/2 doesn't work from looking at the plot. And you could also plot the other equations and figure out similar conclusions. So those are just a few ways to do those types of problems. The next one is kind of rearranging, like this one where they say put these steps in the correct order. So I use a few kind of common language tricks. For one thing, if there's a therefore in the problem, typically that comes last, something like therefore or hence. If there's something like a suppose, consider, or since, those tend to be one of the first things in there. So that kind of narrows things down a little bit for you. So in this case, we know our last block has to be one of these two therefores. And the only thing that's different between these two statements is this inequality is flipped, so you'll have to figure out which one makes better sense. The first example I actually wanted to talk about here, so we can this one's pretty easy because there's only 3 steps. We can see that there's 2 options for the first step, 2 options for the second step, and 2 options for the last. So you got to think about these inequalities and which ones make sense. Is x cubed greater than x squared, or is x squared greater than x cubed? I'll leave that to you to figure out, but that's typically how these problems work. And then here's another instance of them kind of applying the highest order function to the entire one side of an inequality, which is kind of a common pattern I've noticed that they do. Okay, so finding the order of factored functions. So if we have a function like this, where we have 2 sets of functions that are being multiplied, the best way to attack it is to take 1/2 of it and then find the biggest term, do the same thing on the other half, and then multiply them. So in this case, the biggest terms are these n terms, so we just multiply them, get our answer n cubed. Some of these other ones you might have to think about a little bit or plot. For example, is n log n bigger than n squared, or the other way around? You'll have to figure that out. Same thing for n factorial and 2 to the n. If you remember in the book, those two were actually plotted, so that one shouldn't be too hard. Don't forget about the powers inside of the log not mattering. So that's kind of how to attack those. There's one other problem, I guess 2 other problems here. Right, so you have these different functions and you want to figure out what's the maximum number of operations it can carry out in 1 second if each operation takes 10 to the 9th second. So on these homeworks, always use the hints, especially if you're stuck. This one basically tells you what to do. It tells you solve the inequality f of n is less than or equal to 10 to the 9th. So you can basically assume that it's going to be equal, and for A couple of these possibilities, they're not solvable algebraically. You have to either do it computationally or with some fancy math tricks. One example is this n log n. So one way to do this is to solve n log n equals 10 to the 9th on Wolfram Alpha, and it'll spit out the answer for you. So there's the answer right there. It should match up with one of these possibilities. You could do that same approach for all of these, but some of them are pretty easy, like n equals 10 to the 9th, or even log to the n is another pretty easy one. So that's kind of a tip for this problem. The other one that kind of was a little bit tricky was one on bit strings. See if I can find it here. Oh, I think that was it. Right, so the number of comparisons, big O, estimate for number of comparisons for an algorithm determining the number of ones in a bit string. So if you don't know what a bit string is, look it up and refresh your memory. But it's essentially a string of bits, just like it sounds. But kind of think through this algorithm and think what it's doing. It's going to the first bit, checking is it a 1 or 0. So that's an if statement. If you remember, the if statements are order 1, so it goes through each element in the bit string and does an order 1 operation. And there's n elements in the bit string. So what order do you think that operation is? Finally, some other tips. So always use the hints. There's also this check my work possibility. So once you click an answer on here, you can say check my work, and it'll tell you if you're right or wrong. You should pretty much always use this because you get one free chance to use it, and it'll help you get a higher score. So definitely use that. One last thing is that there's a table of different bigO runtimes or orders of different common functions on Wikipedia. It has a few more functions than are in the book, and they also have some examples of practical uses of these things. So order n to the c is searching in a KD tree, which is linked here. So anyway, you might want to take a look at that, or at least be aware that it's there, and it might help you in the future. So anyway, we'll talk to you soon with more info on pseudocode and searching and sorting algorithms and a midterm review. All right, talk to you later. Okay, so we start off. By noticing that all of our k's are 0 or 1, so that means x is always positive. So that means we can get rid of the absolute values because both sides of this equation are always going to be positive. So now what we can do is use a property of fractions that is when the denominator of a fraction gets smaller, the fraction overall gets bigger. So we can take our f of x, which is this, and say that it will always be smaller than the same thing without the 1 in the denominator, because as the denominator gets smaller, the fraction gets bigger. So we can cross out one of these x's, and now we have x squared over 2 plus 1. So we'll start off with the k equals 1 because it's 3 of the 4 possible answers. So what that means is x is greater than 1. So that also means x squared will be greater than 1. So we can take this equation and we can substitute in an x squared for the 1 and say that that will always be greater than x squared over 2 plus 1, because we just said 1 will be less than x squared. Okay, so now we see that our f of x has to be less than this equation, and if we simplify that, it equals 3/2 x squared. So that's pretty much how you can do that problem without substituting in numbers. There's one other way you can also do it, which is to plot the equations. So I've already plotted the g of x and the f of x here. So you can see that with the coefficients, with c is 1, these things cross over right about 1. So I think that was c equals 1, k equals 0. So we can see that in between 0 and 1, actually our f of x is larger than the g of x, so that cannot possibly be true. We can also then plug in these coefficients and see how they look and see which ones actually make sense and which ones don't. So at least for this c equals 1/2, anywhere above x equals 1, we can actually see our f of x is greater than our g of x until we hit about 4. So we know that the 1/2 doesn't work from looking at the plot. And you could also plot the other equations and figure out similar conclusions. So those are just a few ways to do those types of problems.